Thanks, Andy. It's great to be here. Thanks to everyone who put this together. Does everyone have a handout? If you don't have a handout, there's a stack up front here, and it looks like they're just about enough to go around, maybe a few extras. I should say the handout follows the talk pretty closely. There may be a few times during the talk where I'll refer to something that's on the handout rather than scrolling back a few slides. But otherwise, the handout is mostly there as something to hold on to and scribble notes on and maybe look at when you're getting ready to ask a question during the question and answer period. Before I start on the talk, I might tell a funny story related to some of the comments Andy just made. So I've been this thing called a professorial fellow the last few years. There's a variety of titles involved here. And that contract's coming to an end. And so recently I received a nice letter from Human Resources here at University of Edinburgh apologizing for my having been made redundant, offering me lots of ways to kind of help me with this career transition, including meetings with career counselors and all this sort of stuff. So since I'm talking about groups and organizations a bit, it seemed like it was reassuring to me to know that bureaucracy works the same way in Britain as it does in the US. And I got a good laugh out of it. All right, I'm going to talk about individuals as group minds, sort of distributed view of individual level cognition, and then groups as individual minds, and what it would kind of take to establish that, what we're looking for when we ask whether a group as a collection of individually thinking subjects could itself be in a single cognitive state, whether a group could have a memory, not whether like the individuals have memories and somehow they add up to something. What I mean is whether the group as a collection could be in a single state in just the way that my sort of brain as a collection of bits might think is all put together in a single state. My body, whatever you think the individual subject is in the human case. So that's the sort of question on the table. But I'm going to come at this by talking about a model-based theory of natural kinds. It's really a model-based account of what kind of evidence we would have for asserting that two things are of the same natural kind. But this will become clear as we go along. So it's going to be this sort of connection between sort of thoughts about cognition in the individual, thoughts about cognition at the group level, but also thoughts about what these kinds are. What is it for something to be cognitive in just the broadest sense? In a way that we might call generic. Cognition as a generic kind is something phrase I'll use sometimes. All right, so here's what I'll be doing, questions I'll be asking. First of all, what is it for one process to be of the same generic natural kind as another? This will play an important role, as I was just saying. I'll be asking what a cognitive process is. I'll be using this sort of interchangeably with questions about cognitive states. I take cognitive processes just to be causally connected series of cognitive states. So there's no special process ontology that's separate from causally connected series of cognitive states, which allows me to talk about the two things relatively interchangeably. I want to ask whether cognition or cognitive processing is a natural kind, whether that's the sort of thing, I don't know, whether it's a natural, really generic kind, whether it's the kind of thing we can make sense of as being shared, say, by us and by groups of us's and by Martians and groups of Martians and whatnot, as this very overarching kind that could take many different forms. And I want to ask whether groups engage in cognitive processing. So this is more a matter of setting themes, I guess, than a formal outline. You'll see as we move along. Come on, computer. All right, so regarding question 4, what was question 4? Do groups engage in cognitive processing? Here we get some of the more specific possibilities I want to consider. So one possibility is that groups engage in the same specific kind, to make this bigger, sorry. Groups engage in the same specific kind of cognitive processing as humans. For example, remembering, reasoning, problem solving, emotion-based cognizing, and thus presumably the same kind of cognition as humans. Okay, what's that all about? So you might think that there's this thing, cognizing, that we do. And that overarching kind of having cognitive processing or being in cognitive states is, has specific species or other kinds that are cognitive. So remembering is a cognitive kind. Right? Language processing is a kind of cognitive processing. Right? So one way in which a group might engage in cognitive processing, like one basis for saying the group cognizes, is because the group does the same stuff humans do with regard to these specific forms of cognitive processing. Groups remember in just the same way we remember. Groups process language in just the same way we process language. Groups have conscious states in just the same way we have conscious states. Right? So that's one possibility. I realize now that when I change my display, I get this weird shading here. So this may have something to do with the capture that we're working on, but I'll just go back to viewing it here on the screen. My old eyes prefer a bigger display on the screen, but I'll make do. So the second possibility is that groups engage in different specific kinds of cognitive processing, remembering, et cetera, but the same kind of cognizing. That is, groups cognize in the sense that they instantiate, or their processes instantiate just the same natural kind cognizing that we do, but it takes different forms. That is, there are processes that groups engage in that may not be exactly like human remembering or what it is for a human to be conscious. Maybe they're similar enough, though, that we might give them the same names and sort of put an asterisk next to them and say, well, it's not exactly like the way we do it, but it's still cognitive nonetheless. And it's still a kind of a form of remembering, even though it's not really remembering as we remember or attending as we attend. So it might be, that might be what's going on. And under that category, we want to include the possibility that groups cognize. But when we go to identify the particular forms of cognitive processes, we realize that they're so different from human remembering and human attending and human language processing that we don't even want to use those terms at all. We just want to invent new terms for the kinds of cognitive processing groups engage in, even though they still engage in cognitive processing. I want to consider this, I'm including this not just to be a kind of analytic philosopher trying to cover all bases and make all distinctions or anything like that, right? That there is a standard kind of, I think, reaction to skepticism about group cognition. I tend to be sort of a skeptic about this stuff. Sometimes what people will say is, yeah, fine, Rupert, group level processing is really quite different from individual level processing, but it's cognitive nonetheless. In some sense, it's still cognitive, even if the particular kinds of processing are very different, right? And that's the sort of thing B is meant to cover. We'll come back to that. All right, C, groups engage in different specific kinds of cognitive processing and a different kind of cognition, in which case there is this generic kind cognizing that humans engage in only one species of. This is the possibility that I'd really like to get my head around and do something with, and I'm not sure I can, right? It's the idea that not only are the specific forms of processing that a group engages in different from human remembering and human attending and human language processing, the very thing cognition, that abstract kind, comes in different flavors. And so we could go through all the sort of work we've done in cognitive science to try to figure out, maybe in the first instance, what human cognition is. And we form a kind of what we think of as a generic definition of what all these cognitive processes in humans have in common. So we get this kind of overarching definition of what cognition is. And then somebody says, oh, but there's an even more overarching kind that this human cognition is just one species of. Right? And that's a possibility that I think some people have in mind, but it's a different one to flesh out, a difficult one to flesh out. All right, well, this has been very abstract. Let me try to give you something a little more concrete to get your hands on. When I talk about natural kinds, generic natural kinds, and talking about some kind of hierarchy of kinds, it's like, I'll talk about natural kinds in the first instance, but I use this relatively interchangeably. There are a couple of niceties here, but I use this interchangeably with natural properties. The idea is just sort of the things that show up in our best science, the things we think we're trying to find when we're doing science, the properties. I mean, maybe there are no objects, so there are no kinds of objects, who knows, right? They're just fields and properties. I don't know, I don't want to presuppose what our best science is going to find in the end. But whatever it finds, those are the natural kinds / natural properties that actually exist out there, right? But here are some examples from our, beginning science classes. Right? Oxygen, carbon, and lead are not generic natural kinds. I'll qualify that in a minute. They just seem like, they're elements. But being an element is a generic natural kind, right? It's an overarching kind that has particular species. They're elements. And what are the elements? Carbon, oxygen, lead, hydrogen, helium. Now, if you consider isotopes, then maybe carbon and lead and oxygen are themselves generic in a way they have more specific versions, right? But that's the idea. There's a hierarchy of natural kinds, and anything that's not at the bottom is a generic kind. Proton, neutron, and quark are not generic kinds, right? Because they have kinds. There are different ways, 6 different quarks, I think, kinds of quarks. But being a subatomic particle is a generic natural kind. So there's another example. Get your head around. Generic kinds are kinds that have kinds as their species, right? If you want a definition. Right? That's the idea. But these can be more or less generic. Subatomic particle is more generic than, I meant to take that off. Quark, sorry. I put this up here thinking, yeah, quarks are fundamental particles. They're part of the standard model, basic particles, but then, of course, you get 6 different kinds, so I apologize for not deleting that. But the idea, I hope, is clear enough. And now I want to explain how we identify kinds with an eye particularly toward the identification of generic kinds. So I'm going to present something all right, I'm going to present a picture of natural kinds that I call the tweak and extend model of natural kinds. So it's typical in successful sciences that an initial, typically simple model of some paradigmatic phenomenon succeeds well enough, then related phenomena are modeled by the tweaking of the initial models. Terms are added, parameter values adjusted, new elements are tacked on. Here's some examples. Harmonic oscillator, dynamical systems-based modeling of action perception loops. I think something I added to the handout that's not on here was something I heard from Margaret Morrison a couple weeks ago. She gave a talk here about modeling perspectives on nature. And one of the examples she used was the example of turbulence. As she described it, there are 2 generic models of turbulence and 50 specific fleshings out of these 2 generic models. And so that would be another kind of example. But, to keep it simpler, I'm not going to talk about 50 different versions of a model. But you might start off with a basic equation for a harmonic oscillator, and then you say, but, sometimes we want to take friction into account. And so you add a term for friction. And then you say, but in some cases of harmonic oscillators, there's an input force, right? So you want to add a forcing term, right? But sometimes the force isn't constant. It might be sinusoidal, right? So you might be on a swing, right? American-style swings, anyway, work like this. You pump yourself back and forth, and it gets swinging, and you swing your legs back and forth, and your body weight, right? And so the energy that's entering into the harmonic oscillator system is not constant. It has the form described by a sinusoidal function. So this is what I mean by tweaking and extending. You have a model, and then you add parameters, you change values of parameters, maybe you add some new elements. And here's a slightly, maybe more detailed example. This comes from the domain of cognitive processing, but that's not important. I use this as an example from the domain of cognitive processing because I assume people here are interested in cognition, and so they're familiar with, or likely to be familiar with, parallel distributed processing models. But this is just one example from the sciences. I could have just as well gone through the harmonic oscillation case. If you want to see a kind of cool case, in a more physicsy case in the domain of cognition, Tony Chimero in his book Radical Embodied Cognition, says this about this kind of thing. He doesn't use the language I use, but he lays out a sort of basic form of an equation that can explain a lot of dynamical interactions with the environment, and then sort of adds terms to it as he goes to model more and more complicated cases. Right? But the equation has the same basic form going forward. All right. Well, here is something said many of you will be familiar with. Major aspects of a parallel distributed processing model were laid out in 1986. This is going to be taken, a quotation at the end, but this is taken, or citation at the end. This is taken specifically from Rumelhart, Hinton, and McClelland's early chapter in the PDP Bible, Volume 1. So what's a parallel distributed processing model? Well, you've got a set of processing units. You've got a state of activation, those units. You've got an output function, says what gets spit out of one of those units when it fires. You've got a pattern of connectivity among the units, which units are wired up to which other units. You've got a propagation rule for propagating patterns of activities through the network of connectivities. This unit might fire and spit out a certain amount of activation, but what happens as it goes down the wire, so to speak? You've got an activation rule, that's something that sort of sums inputs at the unit and then determines when the unit's going to spit out, when the unit's going to fire, right? So to speak. And you've got a learning rule that governs changes in the network, the most famous of which is the backpropagation rule. Right? And this is a list that Rumelhart, Hinton, and McClelland actually make on page 46 of the first volume of the PDP Bible. How would you tweak and extend this? Right? Well, this is typical sort of thing that happens in connectionist modeling. Right? You construct a PDP model of, say, a categorization task using a step function as an activation rule. So a step function says, here's activation coming into the unit, here's activation coming into the unit. Here, I'm moving along what's supposed to be the x-axis for you. And the response is flat, 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 flat. And then you get to a certain sum, maybe 1, could be set anywhere though. And then immediately, the function that describes the output of the unit or the activation level of the unit shoots up, right? And then levels off. Right? So there's just one point where the activation of the unit steps up. Right? But you could tweak this model. Perhaps the model data related to a different kind of task. That's typically what happens, or a richer data set on the same task, by replacing the step function with a sigmoid function. So that maybe as input comes into a unit, input builds up, you see the activation start to build up. And then input gets to a certain level, and there's an increase in acceleration, you might say. The increase in the level of activation starts to come very quickly, and then it levels off, but it doesn't level off entirely. Right? So some of you are familiar with this sigmoid shape. Right? Point is not, that the details of the modeling aren't all that important. I haven't given you a detailed case. Right? But the idea is this is an element from the list of components of the model, activation rule. It has proven very useful in PDP modeling to sometimes use one rule and then to refine, change, extend, tweak the rule. Right? These two models bear a tweak and extend relation to each other, so the two processes model are instances of a single natural kind, I would claim. A single natural kind is parallel distributed processing. Now, if that were your theory of cognition, then they'd be two elements or two instances of a single natural kind being cognitive, but I'm not committing to that. If you might have noticed earlier my description of the tweak and extend approach to discovering natural kinds, or discovering that we've discovered them. You might have noticed addition of elements. So what you get, say in PDP modeling, is the addition of a characteristic kind of layer. As PDP modeling went on for 10 years or so, somebody said, well, wait, let's not just have 3 layers of connected network, of connected units. Right? Let's add a recurrent layer, right? A sort of short-term memory layer. So you've got the 3 levels, and then in these simple recurrent nets, you've got this sort of side level that saves a memory of what was going on at a hidden level at the last time step. or can save a memory of what the input was at the previous time step. And so, this is the kind of thing I have in mind when I talk about tweaking and extending. I'm going on about it, but part of why I included this in previous publications and such is because I think it's just right. If you just look at the way science is done, this is just how modeling works across a variety of sciences. Now, whether it somehow captures the essence of what it is to be two instances of the same natural kind, I don't know. I take it that to be, the essences of the natural kinds, have they such things, are given by the sciences themselves, maybe. Maybe read off the models themselves. What it is to be water is to have, one oxygen, 2 hydrogen molecules bound together, right? And that might be read off a single model. But I'm asking this different question. What evidence could we have that two processes or two states are of the same natural kind? In particular, when we're thinking about these generic kinds, whose instances won't be exactly the same. Right? Maybe the way you remember is different from the way I remember, but certainly the way the kinds of hypothetical Martians that get discussed in philosophical thought experiments, they remember in different ways than we remember. Right? And how would we what would our justification be for claiming that they're both instances of remembering? Right? And this is as a naturalist, taking my inspiration from successful natural science, this is sort of the best I can do. All right, so just an explicit statement of what I've been saying. We have conclusive evidence that two kinds of processes or states are instances of the same generic natural kind if they play analogous roles in successful models from the same family. I say if, I want to leave open the possibility that there are other ways to get this kind of evidence, but that's just my being cautious, so far as I can tell from looking at the working science in a variety of areas. It's an if and only if at this point, anyway. This is really it. Models are in the same family when they bear the tweak and extend relation to each other that I've been talking about. And so two processes are of the same generic natural kind when our best models of them bear a tweak and extend relation to each other. So I want to shift gears and talk about the nature of cognition now. So if we think, let me remind you why I'm going to do this. If we think that groups might be cognizing, even though it doesn't really look like what we do, then presumably what we'd want to do is find a natural kind cognition that we share with groups, even if it's not quite the same. Think of, if some of you are having trouble sort of getting your head around that, the stage setting there and the motivation, just think about a particular kind of difference. Like if groups are cognizing, then presumably they're acting, right? Cognition is at least largely for action, even if it's not only for action, right? Cognition involves the control of action to a great extent. Right? How do humans act? Well, here's a commonly held view. Humans act partly by issuing motor commands, an efferent copy of which is sent to a unit that runs a simulation of where the body's going to land when the motor command is executed. And then that simulation can be used for various things, like the correction of the motor command. If it looks like your hand is going to knock over your coffee, right, a corrected motor command can go out, so you adjust a bit. Right? You might not buy that forward modeling story about motor control, but the point is, that's the sort of kind of level of detail that cognitive scientists go into when they're trying to figure out how human cognition works. Question, what are the odds that that's going to appear at the group level? That you'll have a corporation or a court or a team that has like a forward model unit set up. And it's not impossible. Right? There might be, in that room in the basement at your corporate headquarters, the group of people who act out simulations of what will happen when the corporation issues motor commands. But this doesn't seem like what's happening now anyway. And so what many people want then in the face of those kinds of objections is an account of cognition that's general enough to apply to humans and corporations, even though they're the kinds of differences I was just meaning to highlight, emphasize. But I should also add, though, that they have to be sort of cognitive scientifically interesting. It has to be a cognitive scientifically interesting conception of cognition, right? For it to be, I think, of interest to naturalists who are trying to understand the mind. You know, there's one way to kind of unite us and corporations is the kind of strategy that philosopher Austin Clarke used 20-some years ago. He has a nice paper in Journal of Philosophy called Beliefs and Desires Incorporated. And he basically says, you know, if you can apply belief-desire psychology to a corporation, if you can look at a corporation and say, it wanted to increase its profits, it believed that by releasing a new product, it could increase its profits, therefore it did release a new product, right? Then it's a mind, because that's how we understand each other. Right? But that sort of practical syllogism psychology isn't really what we do in cognitive science. So if you're interested in a cognitive scientific conception of cognition that's going to apply to the human and the corporation, you'll need to do something more kind of detailed than using a practical syllogism. You know, if you believe that you make more profits by developing a new operating system and you want more profits, then you'll develop a new operating system. It's got to be sort of more articulated than that. All right, so that's what I'm shooting for. Start off with some methodology here. Cognition is whatever distinctively explains intelligent forms of behavior. That is, whatever specially accounts for the relevant data of cognitive science. So I'm just kind of brutally naturalistic about this. Cognitive science is a science no different from any other science. You know, we look at a bunch of phenomena that we think are somehow related to each other. We might have very strong intuitions about which phenomena are related to each other. Maybe that's how it is in meteorology. We have a really good sense of what weather is. You know, it's that stuff we encounter every day when we go outside. Nevertheless, once we start doing the science, things may turn out quite differently than we thought. All of the phenomena that we grouped together as meteorological phenomena might turn out to be of two very different kinds. Right? And the things that we group together as cognitive stuff, we may think we'll get a unified explanation, but they might not. Right? So it might be that the data that we have collected together, you know, human creativity, think of this in terms of outward observable behavior, human creativity, human language use, human experimentation, right? Human, the ability humans as groups seem to have to take, drawings on a piece of paper and turn them into these big buildings that bear a structural resemblance to the thing on the drawing, right? There's a lot of stuff humans do that's really impressive, and you might think it's all of a piece. Right? And what that means, in my book, is that we've done the science. When we've done the science, we will find a single unified account of all these phenomena. Right? But that's not typically how science works, or at least frequently enough it doesn't. Right? You'll get cases where some of the data that we thought was in the same domain as other bits of data really turns out to be explained by a very different sort of model. You say, we thought that was an electrical phenomena, but it's not really. Right? Because we did the science and we realized, 9/10 of the phenomena could be unified under one model. You say, oh, now we know what electricity is. Oh, but there was this other bit of the data, some other phenomenon we thought was an electrical phenomenon that we now just have to recategorize. Right? So I'm not taking it as sort of a priori that we know what cognition is or that we know what the cognitive data are. I'm just assuming the kind of methodology that gets used in any sort of science as it's born and as it develops. There's an intuition about the set of phenomena that make up a domain. We think they make up a domain. We think that there will be a single unified theoretical account of them. But how that interplay works out, it can go all sorts of different ways. Right? All right. I mentioned some of these examples. The data are, at a first pass, instances of language use, theory construction, the attendant manipulation of nature, problem solving, all sorts of, think about playing games or whatever, products of art and architecture, social interaction, correspondence of behavior at a later time with earlier causal interactions, so that's a way of describing learning and memory. This is a long list of things that we think are interesting and important and somehow express human intelligence. Well, I claim, argued in the past, that the common thread to the modeling of all these interesting data is the identification of an architecture, to speak pretty loosely. So I claim that all successful forms of modeling in cognitive science, doesn't matter what stripe, computational, connectionist, subsumption-based, dynamical systems-based, brute neural modeling, evolutionary robotics-based modeling, I didn't put that one on the list. When you go through all this stuff, what you get in the model, aside from the data to be explained, because that technical sense is always part of the model, what you get in the model is a distinction between the sort of persisting elements, kind of stuff that Hinton and Rumelhart were describing when they described the components of a connectionist network. Right? You get the sort of collection of persisting units, and then you get the stream of changing environmental conditions. Right? In the case of the human cognitive system, the passing parade of stimuli. Right? And this is the sort of thing you see over and over again. Someone's giving a dynamical systems-based model. They say, here are the basic processes. Here are the values in the environment that change. Here's the way that at least if they've got an implementation of the dynamic system, here's the way the parts are connected such that they give rise to these dynamics. That's the most interesting and tricky case, but in the other cases, I think it's pretty straightforward. Computational systems, definitely that's where the language of architectures comes from originally, right? You've got these memory registers and these basic operations, these speeds of processing. All right, so I want to call this posit an architecture, generalizing this terminology from the computational realm. It's a relatively persisting collection of mechanisms that contribute in overlapping subsets to the production of a variety of forms of intelligent behavior. I think this is where cognition happens, in the architecture. So at the very least, this could be turned into a necessary condition for states being cognitive. Right? We've got a central distinction between two kinds of causal contributors to the production of intelligent behavior. And the necessary condition based on this central distinction of cognitive science is this: that the state is cognitive only if it's a state of a mechanism that's part of cognitive architecture. A cognitive process is composed of a causally connected series of states. I mentioned that earlier, so I'll ignore that. So, maybe a little more background would be helpful. Many years ago, I got very interested in embodied notions of cognition, right? The way in which sort of the bodily dynamics influence higher level models of cognition. And in fishing around in this literature in the 90s, as I came across Andy's work over and over, read lots of this stuff, and it culminated with the epiphany of sorts culminates with Clark and Chalmers' 1998 paper, The Extended Mind. Right? And at that point, I went, no, that's going too far. That's so weird. But I was open-minded to this, and some of the stuff I wrote at the time was kind of, well, maybe it's extended, maybe it's not. But eventually, it drove me to this picture. I said, well, look, we do have lots and lots of things that are contributing to the performance of intelligent behavior. Some of them are reasonably considered background conditions, the existence of air pressure, the light from the sun, something. Everybody wants to bracket those. They don't even play a role in most of our cognitive models. They're just assumed to be present, right? and left out. Right? And then we want, whether we call these things cognitive, non-cognitive, or whatever name we want to give them, we want to separate the remaining causes into two categories. The ones that are A and the ones that are B, right? And because in some sense, at least one way of trying to understand what Clark and Chalmers, other proponents of the extended mind, have been up to is they wanted to say, look, there's all this stuff that goes into the A category. We usually call it cognitive. You know what? A lot more stuff goes in there than you would have thought, right? People's external tools and props, the hard drive in their computer, or whatnot, right? These things are part of the first-class causes, you might say, although I don't really want to include a value judgment, right? And then, there's still bits of the environment that might contribute to the production of intelligent behavior. Otto's getting himself to the Museum of Modern Art in the classic thought experiment, right? There's still things in the environment that contribute to that, but that aren't part of the cognitive system. or aren't cognitive, aren't mental. Right? But there are a bunch of things that people didn't used to think were mental or cognitive that should be put in that category. And so really the project for me was to distinguish causes in category A from the causes in category B. Right? And this, to my mind, was the only way to do it. This is what I came up with, right? Is that it's going to be the stuff in the relatively persisting, relatively integrated set of mechanisms that we would identify with the architecture, the stable bit of the model from the passing bits of the model. And this is a neutral criterion and might, in the end, lead to or support the claim that there's lots of extended cognition. I think if you make a model of how I behave, one of Chalmers' favorite examples, iPhone, might end up being there as a consistent part of the architecture nowadays. 20 years ago, when I started thinking about this stuff, didn't have an iPhone. So, you know what, this is neutral with regard to that issue, but that's the motivation behind it. And the thought was, the not neutral thought was that when it comes to modeling, you know, language acquisition and most forms of problem solving and concept development, and the persisting architecture would be most of the time inside the skin, so you'd get a non-extended result. But that's the part that's still sort of, you know, a matter of debate, I think. All right, so some background. What I'd like to do now, if the iPhone will let me, is talk a little bit about what I think an integrated system is. iPhone says no, so I'm not going to do this in detail. But what I've done on these two slides, and you'll see it on the handout, is I've gone through a kind of 7-step procedure. Doesn't need to be thought of procedurally, but I think it's easier to get your head around when you think of it procedurally. It's a procedure for sorting the mechanisms into these two categories, the ones that are part of the architecture and the ones that aren't. Right? But what I particularly wanted people to take note of is not, you know, how subtle and wonderful this procedure is. What I wanted people to take note of is that this is a kind of functionalist characterization. I'm saying you have cognition going on in you if you have a cognitive system. Right? What's a cognitive system? Well, you have a cognitive system if there exists a set of mechanisms that fit this measure of integration. And the integration is functional in the sense that it doesn't appeal to the particular matter that it's made of. You just have to have a system that has these certain relationships characterized mathematically. It doesn't have to be made of carbon-based atoms. It doesn't have to be made of silicon. Made of anything that can make up a set of mechanisms interrelated in this way. All right. So if this hypothesis about the nature of individual cognitive systems is correct, then the human self or cognitive being consists of a somewhat loosely organized collection of mechanisms. So this is very important. There's actually a second important moral from those two slides I'm skipping over, is that I don't want to say anything of the following sort. I don't want to say, and you know, absolutely, you know, stay away from this kind of philosophizing for the most part. I don't want to say, look, the mechanisms out there aren't part of your cognitive system, because it doesn't seem to me like they're part of my cognitive system. That's, you know, I used this terminology of being weird earlier, but that's tongue-in-cheek, right? These kinds of categorizations have to have a principled basis. Right? And so I think that when you approach things in that way and just say, hey, there are all these causal contributors, let's try to figure out what separates them into two categories. The kind of unifying principle you get, the kind of unifying principle that's there on your handout in the 7-step procedure is, it's not that unifying. It's nothing to do with like a single conscious perspective or an executive controller that makes everything else happen. It's a pretty loose collection of mechanisms. You've got all these bits of your brain that do different things and bits of your environment that do different things, right? I want to emphasize their co-contribution. That is, some things are much more likely to co-contribute to a variety of forms of intelligent behavior than other collections of things. And when you look at the overlapping subsets of these important contributing groups, what emerges is a kind of privileged collection of these. So, you know, there's a when I read, I'm using short-term memory, I'm using long-term memory, I'm using word form area, I'm using various other parts of my visual processing system, right? So there's a collection of mechanisms that are contributing to produce the data. Like, I'm reading out loud, so the data would be my words and their correspondence with what's on the page. Right? Lots of other cognitive activities, we might say, production of different forms of intelligent behavior, will involve some of those mechanisms combined with other mechanisms. Right? So you get this pastiche sort of collections, sort of overlapping collections. Right? And then at the other end of the spectrum, you'll have one-off tools that are good for one thing, and one thing only. Right? So I suppose I could use my extension arm that I reach up and close the windows with for other things, but it might be that all I ever use it for is that one task. So it's not going to be kind of part of many of these sets that overlap with each other to produce a wide range of forms of intelligent behavior. Right? So what I want to really to give you a sense of there is how loosely connected even an integrated system can be. An integrated cognitive system, your brain, if you want to think of it neurocentrically, is made up of a bunch of mechanisms that in many ways are loosely connected. And that's the image of the individual mind as a group mind. And this image of this kind of loose connection of mechanisms, even though they're more tightly connected to each other than any one of them is to my extension arm that I used to open the window, this loosely connected set of mechanisms might look sort of like a group mind. Right? If that little integration is all it takes to have a cognitive system, then surely a group could have one. Right? Groups are integrated in these ways. Right? So let's get on to groups as individual minds. So this picture I've been describing might suggest that it's easier than sometimes thought to establish a group subject of cognitive states. That is, a single subject of cognitive states that itself has two or more components with their own cognitive states. For just the reason I gave a second ago. That, if you can have a cognitive system with a bunch of these parts that kind of contribute in overlapping subsets but don't have, a really strong central controller that's telling them all what to do. They operate together by some sort of delicate balance of forces pushing and pulling on each other. A lot of time people talk about biased competition among different processes in the neural system. Right? There's just a ton of stuff going on in there at the same time. This is the Undermind part of this talk. There's a little more in the second talk. Then if you've got that on the individual level, then you can see that swarm of interacting mechanisms producing outcomes at the corporate level and at the team level, at the level of a union or a government. So after all, being cognitive is to have a cognitive architecture. Having a cognitive architecture is characterized as a second-order property, as having some collection or other of mechanisms related in a certain way. Well, it seems plausible enough that models of certain group-level activities will satisfy this description. I mean, think about how weak the description is. There's this, functionalist point I was making a few minutes ago. It's just that there exists these parts, and they interact in a certain way to produce the outcome. That way of interacting isn't all that demanding, so you should be able to find an architecture at the group level. All right, so here's a potential objection. You might ask, is everything that appears as a common element in a family of models a natural kind? Certainly, if you interpret common element broadly enough, the answer will have to be no. Right? If the appearance of a beta counts as a common element, then a whole bunch of different models that happen to have betas in them, that is the inscription of Greek letter beta, right? They will all have, they will define a natural kind by their interrelation. They could, right? But fonts don't matter. The choice of a particular Greek letter to represent a quantity doesn't matter. It could be quite misleading. You might choose a a letter to represent one kind of quantity, I might choose it to represent a different one. This is a toy example, but I just want to make it clear that this isn't a completely pointless question, that obviously the answer is yes, and then we want to figure out when we've got artifacts and when we don't. As in the model-based criterion of sameness of kind, is that merely a necessary condition but not sufficient on our having discovered natural kinds? Do we have to add something to the criterion to weed out artifacts? Like add something like, oh, but fonts don't matter, or things like that. Might a common element sometimes be an artifact of our modeling? Under what conditions would we treat a common element as an artifact? How do we write up these exceptions? Now, in the particular case at hand, the problem isn't that there's a font in the model of individual cognition that gets shared in the standard presentation of the model of group level cognition. It's nothing as trivial as that, right? Models are supposed to be identifying structure, like real structure in the world if the model is useful enough, right? And so maybe to make this a more compelling question, one that may actually arise in scientific context, we might ask ourselves, when is a certain structure important and when isn't it? When is a structure a phony structure, even though a structure nonetheless? Right. So maybe you find certain structures when you look at a calendar because we've chosen to represent the year in certain 7-unit increments. Right? So you'll find some structure in there that's really an artifact of our way of representing the year. Right? What you might do is add a causal explanatory constraint. Right? So perhaps the common element or structure must also play a causal explanatory role. It must explain in some deep sense the phenomenon modeled. Right? It can't just be, like I say, some pattern that you recognize in these two models that's playing no particular role in the fact that the model, most of the model accounts for some of the other part of the model, the data part. And I think there's a particular worry here because I've characterized a kind of second-order relational property, being the state of some mechanism or other that's related to other members of a collection of mechanisms in the right way. And you might think, what does that explain? Folks have had have been puzzled by these sorts of questions in very disparate domains, parts of philosophy of mind and metaphysics and whatnot. You might say, well, a stimulus item's being red or blue, that can explain my response, but a stimulus item's just being colored, right? Is that? I mean, it's true that anything that's either red or blue or light or dark or in some sense has a color, and you can construct a description of what all the colors have in common and say that's the property of being colored, just having a color, right? But does some things having a color really explain much? Or is it always sort of this more specific color that it has, right? And so people puzzle over this kind of thing in metaphysics, sometimes in philosophy of mind. And so that maybe is the kind of, if you're familiar with those debates, that might be a way of motivating this concern here. Right? You can use logical formalism to introduce all sorts of properties. Right? And the question is whether you've really captured something important about the world by identifying them. Well, it's a possible solution. It's so important it spins around. Specific actions of an individual human are part of a suite of that entity's actions which, taken as a whole, exhibits, across time and context, certain very general patterns to do with, for example, flexible problem solving and cross-temporal coordination. The idea is to identify somewhat abstract properties of the data themselves that need explanation. It's not just that subjects in this experiment were able to separate the words from the non-words with this certain error rate, with this average response time, right, in one condition, and this average response time in a different condition. It's not that. It's the general ability to sort things into categories, maybe, right? The intelligence of sort of being able to sort things flexibly, lots of different things, so now I have to pool a bunch of experiments together. Right? To be able to engage in this kind of flexible categorization. Right?
So you might think that being cognitive explains the appearance of that suite of actions, right? It might be that collections of kind of counterbalancing, variably cooperating mechanisms provide the only or especially effective way to produce a variety of forms of intelligent behavior. Anytime you've got sort of flexible intelligence, it might be that this picture is given the way our universe is constructed, the materials we have, the forces that we have. It might be that this picture is present. Anytime you've got a critter that can engage in sort of flexible problem solving, you've got a set of mechanisms that contribute in overlapping subsets to a variety of forms of intelligent behavior. So it might be that this construction that I've been promoting really does play a causal explanatory role. It's not an artifact of the modeling process. Right? The fact that that structure appears in a bunch of these different models is evidence that that's a natural kind. All right, so how do we wind up with regard to group cognition? It's going to be a sad ending in some ways. I'm sorry. With regard to the actual groups in our world, corporations, clubs, courts, political parties, the situation is challenging. Largely because they don't seem to engage in the same specific forms of cognitive processing we do. And when we recognize that, I was trying to emphasize earlier with my forward model example, right? We recognize that and we go searching for some other commonality. That's where we get into trouble, right? So if you look back at your handout, this is the one place where I intended to refer to the handout. You look back to what was 1B1, right? 1B1, 1B, clarification, 1. Groups engage in the same specific kind of cognitive processing as humans. For example, remembering, reasoning, problem solving, emotion-based cognizing, right? That's why groups cognize, because they do the same thing we do at that more specific level. And those are species of cognition, so you get cognition out of it. But that doesn't seem to be on the cards. So what are the chances that they share an architecture with humans? And thus 1B2 holds. So there's this possibility, let's look back at 1B2, that groups engage in different specific kinds of cognitive processing. They don't remember the way we do. They don't process language the way we do. Maybe even like the semantics of their representations is different from the semantics of ours, you know, the sort of theory of content that applies. I mean, there'd be lots of differences like that. But still, they engage in the same kind of cognizing because they too have a collection of mechanisms, does this sorts of, is integrated in the way ours is. Right? Well, when a corporation makes a decision by asking the opinions of a variety of fully autonomous cognitive agents, it is not engaging in decision making of the same kind as humans. But is it some form of cognition nevertheless? That's the way I'm putting my question. But I think we have to come at this behaviorally. Right? And why? So stop there. Why do I want to come at it behaviorally? Right? Because notice that the collection of mechanisms is partly individuated relationally. It's partly individuated by the kind of stuff it causes, right? A variety of forms of intelligent behavior. It's a bit like being a planet. Right? So a planet isn't just to have a certain shape or a certain mass or a certain motion. It has to be part of this larger system. It has to be, in our case, part of the solar system, but a system of things that orbit around other things. Right? And so this is problematic partly because the behavioral output of the groups is very different from humans. Right? So we don't have parity of explananda. Right? So you think about, the problem with some groups is that they just do one thing. Right? So they're going to be out because they don't exhibit a variety of forms of intelligent behavior. So the stock market is an example people sometimes use as an example of an intelligent group. Right? But the stock market seems to do a very small number of things. Right? It, you might say, predicts the future profitability of companies, right? To put it pretty crudely. Right? But it predicts it by assigning values by voting, a voting process. But it doesn't do anything like the variety, it doesn't engage in anything like the variety of forms of intelligent behavior that I described in connection with the explananda that get cognitive science off the ground, from art and architecture to language processing to writing books and constructing theories and doing experiments and so on and so forth. So that's one problem with the behavioral approach. But another problem is that even groups that do a variety of things may not do things that are obviously like what we do. So part of what worries me is this. Here's a sort of picture, is that we've got two, you might think, two parameters here of comparison, two dimensions of comparison. Say there's the behavior, and there's the model that is supposed to produce it. If a corporation or a court's or a team's behavior, suite of behaviors, were like the human suite, like really in detail, or at least compellingly like the human case, then we would have an anchor here. And then we could say, well, however the group does this is going to be a form of cognition. And so, you know, we better find some overarching characterization that includes the human architecture and the group architecture. There's got to be this higher level kind. Right? Or, if the behavior is not the same, we might sort of start from the inside and say, look, we've found what produces intelligent behavior in humans. It's having a certain kind of architecture. And even though groups don't behave the same way, look, some of them have the same architecture. Right? So we've got a dimension of similarity there, strong similarity, that anchors the extension of the kind cognition to groups. Right? But we sort of need one or the other. If you've got different models and different behaviors, then I just think we sort of lose our bearings for the comparison. Right? So having the same behavior is really pretty important. The possibility that remains is the one I just started talking about, right? This possibility that groups engage in different specific kinds of cognitive processing and a different kind of cognition at that abstract architecture-based level. In which case, there would be this generic kind cognizing that humans engage in only one species of. And this is a bit mind-boggling to me, partly because of the generality of the characterization that I gave of the human cognitive system. There exists some collection of mechanisms that are interrelated in this abstract way to each other. And I think, wow, what would be the third-order quantification? Well, I guess it'd be second-order quantification that would allow you to construct a description that subsumes my description of the human cognitive system and the group system as well. Right? I mean, maybe it can be done, but this is the challenge to someone who wants to say, groups engage in cognitive processing. It's not the same kind of stuff we do at the level of remembering, meaning, and attending. And it's not the same cognition specifically as the kind of cognition that we engage in. It's something that we share with groups at a more abstract level, or they share with us at a more abstract level. And I'll say, okay, what's the model? What's the model of something that my model of a human cognitive architecture is one species of? And let's kind of wrap things up here. I don't think that we've got enough similarity in the description of the architectures themselves to make up for the difference in behavior. And that's a worry. We don't have enough similarity in behavior itself to kind of compensate for the differences in the models that produce them. So I think what we should be doing, I said it was going to be a sad ending. I'll make it a little bit of a happy ending. What we should be doing is one of two things. Trying to refine our understanding of what cognition is in general. Right? It's not parallel distributed processing, I don't think. It's not physical symbol systems. Right? These things are too narrow. Right? It's something more general than that. Right? And so we want to refine our general conception of cognition and then look at groups to see whether they do it. Regardless of what behavior is being produced. We might just have to say, oh, wow, there's intelligent behavior we didn't anticipate. Another thing, a kind of positive note to end on, is this idea that maybe a lot of this debate doesn't matter. Right? It's that it doesn't matter in the following sense, not just because, philosophy. But it doesn't matter because lots of the things we want attributions of mental states to groups to do can be done without really saying these things are mental, right? So for example, we might want to hold corporations legally responsible for negative consequences of their corporate activities, right? You don't have to say that they're conscious or they cognize or they have minds. You just have to say these corporations are made up of people. We want them to stop doing that. People will stop doing it if they're threatened enough, like with real consequences, and we have access to the accounts, that the draining of which will get these people fired and put in jail. Well, we put them in jail along with draining of the accounts, right? So, you know, you just rely on a kind of consequence-based strategy to get the results you want without having to say that the corporations are morally responsible for their actions or think or cognize or intend or any of that. So that's one reason this may not be so important. Another reason it may not be all that important, and it relates to some of the things I said earlier, is that many of these questions are still open. Right? So I haven't given you anything like a decisive argument that groups don't think. And even if they don't think, groups still have properties. Right? That is, group dynamics is still a thing, even if those dynamics don't constitute cognition. Right? So you have people like Olaf Sporns, for example, but there are many others who are interested in studying the dynamics of, say, networks, that is, artificial, technologically created networks, like the internet, right? The dynamics of networks that may also apply to the dynamics of brains. Right? It may turn out that if you have a network with a bunch of semi-specialized modules, right, it will run most effectively. Modules communicate with a certain frequency and don't communicate with a certain frequency. There may be changes in the properties of the network that depend on how you change the information sharing properties of the components, right? And these could be interesting factors, right? These could be interesting group level, network level, neuron level, as brain level properties, regardless of whether we say this constitutes thinking, regardless of whether it's cognizing, right? I mean, think about a simple example. A group has a property, a group of people has a property, it's incontrovertible, right? It has a property of its collective mass, right? But just because it has a property doesn't mean it's a cognitive property, right? So we might be interested in all sorts of properties of groups that will help us understand group dynamics better, regardless of whether we call these cognitive properties or not. But the sort of theoretician in me still wants to figure out where sort of the real cognition is and where the other interesting stuff is. Anyway, thanks.